So this is G481 homework booklet question 25. So we've got a velocity vector for a particle moving at 31 degrees to the horizontal. First thing to say is here's a question part, and there's a nice instruction on figure 25.1, show the horizontal and vertical components of the velocity. Had a lot of people who didn't answer that question because they didn't actually look carefully enough and read that. There was no answer space, they didn't bother write anything. You must read the question and look out for these questions where they're asking you to do something on a graph or on a diagram. So we've been asked to show the horizontal and vertical components of that velocity, and here you go, there's a horizontal component, there's a vertical component. The point of components is they're two vectors who themselves are at right angles to each other and which add up to the original vector. How can I tell from looking at this that the components are correctly adding up? Because where one finishes, the other ends. You could of course have equally validly have your vertical one going up there and the horizontal one going across there. The order they're in doesn't matter. But they are vectors, they must have arrows. Components are vectors, all vectors must have arrowheads. Please be careful with that. We're then asked to calculate the horizontal component of the vector. Perhaps the easiest way is to use the formula in the formula book, fx equals f cos theta. You've got to know what all those means. Fx means the component of the original vector in the x direction, and the x direction is simply defined as the direction which is at the angle theta to the original vector. So there's my angle, there's my 31 degrees. As soon as I do that, that makes that direction the x direction. That's why I know that I'm going to choose the cos component rather than the sine component. So the VH is 8 cos 31, it's 6.86 meters per second, 6.9 meters per second. Another way of possibly thinking about that is I know that that's either going to be 8 cos or 8 sine. That's an angle less than 45 degrees. I know that cos gives me the bigger value than sine for angles less than 45 degrees. Cos starts at 1 and goes down at 90 to 0 at 90 degrees. Sine starts at 0 and goes up to 1 by 90 degrees. So because I'm less than 45 degrees, I would expect my horizontal component to be bigger than my vertical component. I can see that very clearly from the diagram. With 31 degrees being less than 45, I can spot that that must therefore be the cos component. Number of different ways of looking at it, but what matters there is that you get the idea, and you get that formula 6.9. You might even want to start right from the very beginning, which should be saying, I know I'm after the x direction. On my right angle triangle, my x direction is my adjacent. The 8 that I've got is the hypotenuse, so I could write that cos of 31 is the adjacent that I'm after, divided by the hypotenuse, the 8 meters per second. So this adjacent side that I'm after must be 8 times cos 31. Awful lot of talking for 1 mark. It's 6.9 meters per second. We've got a ship being pulled by 2 tugs, and again, reading the question, we got the information that the ship's travelling at a constant velocity. The tensions in the cable and the angles are shown on the diagram. Again, must look at that diagram. They're not asking us to add anything to that diagram, but again, that it wouldn't be unusual for them to ask us to do that, so look out for that kind of thing. And draw a vector triangle and determine the resultant force provided by the 2 cables. So what I'm going to do is, here's my picture, and in the way that I'm certainly nagging my groups to do the whole time is to separate out my vector triangle from my picture. There's a vector representing 1.5 kilonewtons at 55 degrees to the horizontal. There's a vector representing 2.14. You'll notice it's a bit longer, and we've got this angle here being 35 degrees. Maybe if you imagine that was a straight line, that angle there is clearly the same angle as that 35 degrees, and therefore by what I'd call a Z angle, that angle inside is also 35 degrees. Now they've been very nice to you here because they've given you 55 degrees and 35 degrees, and that means that those two add up to 90, therefore I can work out that's a right angle. So the nice thing is that those two things are at 90 degrees to each other. Therefore, working out the size of the resultant force becomes trivial, and though it becomes a case of doing it by Pythagoras. F squared is 1.5 squared plus 2.14 squared. F is the square root of the answer you get when you do that. It's 2.61 kilonewtons. It is worth saying that you could do that by scale diagram if you'd measured that out, and they accepted anything between 2.4 and 2.8 kilonewtons. To get the marks for the diagram, the arrows have to be right. Have I mentioned, make sure you get your arrows on your vector triangles. The arrows have to be right to get the marks for the triangle. Again, there's nothing actually stopping you by starting with having started with the 2.14 kilonewtons and then adding on to that the 1.5 kilonewtons. So there and then there, and you've ended up with the same result, but up there. Doesn't matter which way around you do it, but you've got to have those two vectors adding on to each other. So one drawn, then where that finishes, the other one drawn. And the resultant needs to go from the beginning of the first one to the end of the second one. Each one needed an arrow. It's a vector, give it an arrow. These aren't just pretty pictures. So the resultant force was 2.61 newtons, and then really important, again, read the question. I've got state the value of the drag force and explain. That explains why I've got 2 marks here. State the value of the drag force. Well, the key thing was that point we were given, I pointed out right at the beginning, that the ship's at constant velocity. If the ship's at constant velocity, then it is in equilibrium. That means the total force must be 0. All we've done so far is to work out those two forces, but there's also going to be a drag force, and that drag force is going to be in the direction it's travelling. In other words, it's exactly the opposite direction to the sum of those two that we've just worked out. It's in equilibrium, it must be the same size. So whatever answer you got there, hopefully it was 2.61, same answer there. Explain it. Simply the fact that we're told that it's travelling at constant velocity implies, or tells us really, that it's in equilibrium, therefore implies that we've got 0 net force. So from the tugs we've got 2.61 kilonewtons to the right, then the drag must be 2.61 kilonewtons to the left, because those are the only forces acting. So that was G481 homework booklet question 25.